Okay, thank you for the introduction. And again, I'm Luigi, and today I'm going to talk about our latest research activity, which, as you said, regards the benchmarking of reinforcement learning algorithms applied for network-level coordination of autonomous mobility on-demand system across different scales. So first of all, when we are talking about autonomous mobility on demand, we intend a recent concept that aims at bringing together the recent advantage that have been in autonomous vehicle with the mobility on demand concept, in which there is a passenger that requests a drive from an origin to a destination point inside a city, and this request is served by shared vehicles that belongs to a larger fleet that can be provided by any provider. And with the MoD system, we can enhance the benefit of traditional car sharing through the integration of an automated and centralized control, with the main advantage for the provider of the reduction of transportation cost and the increase of vehicle utilization while decreasing the waiting time for the customers. However, when we want to control an autonomous mobility on-demand system, there will be thousands of robotic vehicles that should be routed inside a very complex transportation network that aims at representing a city. And for this reason, there is an increased need of improved algorithms that test to solve some fleet coordination tasks. The state-of-the-art approaches that are used for solving fleet coordination tasks can be mainly grouped into three categories. The first one is represented by the heuristics, which are mainly based on a set of rules. And with this kind of technique, we can be simple, reliable, and efficient, with the main drawback of not being optimally. While with optimization-based strategies, we are able to achieve very high performance, but the main drawback here in this case is poor scalability if we want to apply this technique to a very large network context. Lastly, instead, with the learning-based strategies, it is possible to be efficient and effective, especially in handling the stochastic nature that for sure will affect this kind of problem, but with the drawback in this case of a lack of performance guarantees. Our goal is to propose a methodology that can be applied in real time for coordination of autonomous mobility on-demand system, and that is able to leverage the best of learning-based and optimization-based methods. At high level, when we want to control an autonomous mobility on-demand system, we can split this problem into two main steps. So the first one is the dispatching, which mainly consists in assigning vehicles to a customer request. While the second one is the rebalancing, in which we want to move or not idle vehicles from a certain part of the city to another part of the city. However, to design our fleet coordination algorithm, we decided to split this problem into three steps. So the first one, with the first one, we solved the customer demand matching problem in order to assign available vehicles to passengers with the main objective of maximizing the total profit for the provider. The second step instead entails the determination of the desired distribution of idle vehicles, and in this case we are using a graph reinforcement learning based learned policy pi. And in particular, given the current state of the system that comes out from the first step, so the matching one, the policy pi will output a desired categorical distribution over station of the idle vehicles that will be rebalanced in the third step, in which we convert the desired distribution into actionable vehicles rebalancing flow, solving a rebalancing cost minimization problem. With this approach, we can solve a one-step problem opposite to a full planning problem that is featured by the optimization methods. And with this approach, we have two main advantages. So the first one is the composition of the problem in time, because we can combine the long-term planning capabilities of reinforcement learning with the performance guarantees that comes out the optimization-based method. In addition to that, we are also able to reduce the action space, because we take decision at each station level as opposite to along each edge, as in the majority of the literature. And with this approach, we can significantly improve the scalability of the training and the real-time implementation of the algorithm. In practice, we test our method on real-world data that comes from different cities. And we also tested this approach at different level of fidelity in terms of traffic flow models. In addition to that, we also compared the performance of the proposed methodology both against an heuristics and an optimization-based method. As you can see here from the plot on the top left side of the slide, the proposed methodology, which is represented by the blue bar there, is able to be in pair with the performance that is possible to achieve with the optimization-based strategy, both in terms of profit for the provider and customer demand satisfaction, with a significant computational gain if compared to the state-of-the-art optimization-based method. Finally, to sum up this presentation, we introduced a reinforcement learning-based framework that can be applied for real-time coordination of autonomous mobility on-demand system that is able to combine the high scalability of the heuristics with the performance guarantees of the optimization-based method. In the next steps of this activity, we would like to involve multiple communities with the purpose of democratize the algorithmic development for this kind of problem. And our goal is to create a public repository with different benchmark algorithms to be tested on real-world data and across simulators that has different level of fidelity, going for example, from the microscopic one to the macroscopic one. And please, if you want to know more about this work, read the paper, pass by the poster. And lastly, I want to thank you all for your attention. And if you want to give your contribution, please scan the QR code and feel free to contribute with us. Thank you.